All right, so we're on question 39 now, and this question is, well, I guess first let's read the question. It's a 2-star question, so that's, I guess, medium difficulty. I think that's our first 2-star question so far. And spoiler alert, the next video is going to have a 3-star question, so we'll go through those quick. It says a ball is thrown with an initial velocity v0 up an inclined plane. The plane is inclined at an angle phi above the horizontal, and the ball's initial velocity is at an angle theta above the plane. So let's actually draw that a little better. My circle was not on par here. Let me see. My drawing is getting a little bit better. Oops, that's not what I want. I would recommend checking out, quick little plug, because why not? My Instagram page. Oh, that made it red. Okay, whatever, it's red. My Instagram page, where my drawings are much, much nicer. At least a little bit better. It's actually the ones I use for my notes, so worth checking out. Now the ball's on the ramp. And theta is the angle above the plane. Okay, cool. Choose an axis with an x measuring up the slope, y to the normal, and z across it. Write down Newton's second law using these axes and find the ball's position as a function of time. Show that the ball lands a distance of r, that's the range, of 2v0 squared sine of theta, cosine of theta plus phi, all divided by g cosine squared of phi from the launch point. So that for a given v0 and phi, the maximum possible range up the inclined plane is r max equals v0 squared divided by g times 1 plus sine of phi. Okay, so I've seen some people say this is a really, really difficult problem, maybe a 3-star problem. I don't think it's a difficult problem. I think it's a tedious problem. It'll probably be the longest problem we've done. I'm expecting this to be the longest single problem example I've done so far. So I guess just strap in and trust me that we'll get the answer eventually. So where do we begin? Well, it's worth starting with just a free body diagram. That's always not a bad place to start. Well, we're assuming that it's frictionless. It doesn't mention anything about friction, so it's usually okay to assume that the ramp is frictionless and we're neglecting air resistance. So the only force acting on it is the weight force exerted by the earth onto the ball. And if we drop our perpendicular right here, this angle here is the same angle as the angle of incline for our ramp, which is phi. And then I'm sure you know this is, I'm going to actually denote this a little differently. I'm just going to say the force of gravity onto the ball. And this is the force of gravity onto the ball in the y direction. Both are okay notations. I'm just going to switch it up a little bit. And this is going to be equal to mass times gravity times cosine of theta, because that's the adjacent. The force due to gravity, of course, is just mass times gravity. And then just right triangle trig, adjacent, if you remember, so ka toa. It's adjacent, which means next to. So you can do your ka, basically part of it. And then for the opposite, that's going to be the force due to gravity on the ball in the x direction is going to be equal to mg sine of theta. Now, real quick, let's get the signs right. If we're letting this dot here be our origin, well, our y component is going to be negative, and so is our x component. The y component's negative because we're going down, and the x component is negative because we're going left. So that takes care of our signs. Let's do one more drawing, because I think it's important to draw everything you have first. And let's look at our velocity vector. So we have the velocity vector v naught, and the angle it makes is theta. Well, again, we have a y component here, which is v naught in the y direction, is equal to what? Well, it's going to be the magnitude, which is just v naught, that's our long hypotenuse, times, it's the opposite, so sine of theta. And then we can do the exact same thing over here for the x component. Except now, because it's next to it, it's adjacent, so we use cosine theta. Okay, well, let's go ahead and box some of this really important information that we'll end up using. We know the components of our velocity, and we know the components of our force, which is also important. Okay, so good start. Now what's next? Next, we're going to use, well, first off, let me do one last bit of drawing up here. We're letting our coordinate axis be, if you can imagine, this is your x-axis. It's going along the slope. And then your y-axis is coming up like this. And then the z-axis would be going across. Now, we're not really interested in the z-axis so much, but I just drew it so you can hopefully visualize it. These would be the negative parts of our coordinate system. Okay. So now we have that. Now let's move on to Newton's second law. Now we can break this up into the x and the y. The reason why we're not concerned about the z is because we don't have any forces acting in the z direction. So for what it's worth, I'll go ahead and write that out. Is mass times acceleration in the z. There's no forces, there's no acceleration. There's not much to learn in the c direction. So let's look at the x direction. We can say that the sum of forces in the x direction is equal to mass times acceleration in the x direction. Now, again, in certain situations, we would think of this more as a differential equation. However, it's not necessary here because our force is constant. Our angle isn't changing, phi doesn't change, and the mass and the g, the constant, doesn't change. So we can think of this pretty not too hard, I don't think, just as we would in Physics 1. Well, the force in the x direction, if we go up, we said was minus mg sine theta. So this is minus mg sine theta equals mass times acceleration in the x direction. We can divide both sides by m. And very nicely, we get acceleration in the x direction is equal to minus g times sine theta. So this is the acceleration in the x direction. There's also some acceleration in the y direction, so let's figure that out. The sum of all forces in the y direction is equal to mass times acceleration in the y direction. Well, if we look at our free body diagram, we said that our force in the y direction is minus mg cosine theta. So this side can be replaced with minus mg cosine theta, which is equal to mass times acceleration in the y direction. Again, we can divide both sides by m, and we get acceleration in the y direction equals minus g times cosine theta. Now, why is this important? Well, it's important because we can find the position pretty easily now. What we know is we know x equals x naught plus v naught in the x direction times time. plus 1/2 acceleration in the x direction times time squared. We have this kinematic equation because our acceleration is constant, so it's okay to use this. Now, if we think of our coordinate system, the way we set it up, where our ball's at, the initial position is 0. So x initial is 0. Now we can say x equals, what's v naught, the velocity in the x direction? That's v naught cosine theta. So I can say v naught cosine of theta for this part times time. Acceleration in the x direction we said is minus g cosine theta. So what I'm going to do is I'm going to replace that here. So the minus, that's minus g. We'll just say minus 1/2 g sine of theta times time squared. And there we go. I made a mistake. This is not theta. This is phi. And this should be phi 2. Look at me. Yeah, this is phi. Oops. There we go. Remember, we're using phi from the ramp when we're looking at our forces. And I even drew it in the free body diagram, but then I guess just out of habit, I use theta. Velocity is okay. Velocity is theta. That's better, that's better. And then this is phi. Okay, cool. No mistakes there now. We fixed it. We can do the same thing for y. We can say y equals y naught plus v naught in the y direction times time plus 1/2 acceleration in the y direction times time squared. Y naught, y initial, we can say is 0 following the same logic. And then we also solved for these. So we can say y is equal to v naught, we'll do it in red, v naught sine of theta times time. And then the acceleration in the y direction, we'll say is minus 1/2 acceleration, so g cosine of phi, I got it this time, times time squared. So what we did is we found, and I'll just specify this, we found x as a function of time, and we found y as a function of time. I think that was the first part, was to describe the position using Newton's second law. Write down Newton's second law using these axes to find the ball's position as a function of time. Well, there you go. There's our position as a function of time. If you wanted to write it as a vector, we could say r of t is equal to the x component. So v naught cosine of theta times time minus 1/2 g sine of phi times time squared. And then for this part, we'll put the y. So just v naught sine of theta times time minus 1/2 g cosine phi times time squared. There you go. Okay, so we did that part. And then it says show that the ball lands a distance of r equals 2 v naught squared sine theta cosine theta plus phi divided by g cosine squared of phi from the launch point. Okay, so here's what we need to know. We need to know that when the ball hits the ground, or the plane, when the ball hits the plane, y is equal to 0. So this ball here, maybe it goes up and then it lands here. at that point when it hits, y is going to be equal to 0. So we know if we look at our position function for y, we said y as a function of time is equal to v naught sine of theta times time minus 1/2 g cosine of the phi times time squared. And we can think of this as just being y. This is our y value. We're saying y must be equal to 0 for the ball to hit the ground. So 0 equals v naught sine of theta times time minus 1/2 g cosine of phi times time squared. Okay, well, let's find the time that the ball's in the air. We can divide both sides by t, with the exception of if t 0, which is worth talking about. So I'll do this in red. If t equals 0, what I did was invalid, because what I'm doing is I'm dividing every part by time. Well, you can't divide by 0. If it's any other number but 0, then what I did is fine. But we're kind of not including when time is equal to 0, because when time's equal to 0, that's just where we started. We want to know where it lands. So we know that t's not going to be 0. I'll just put an x in case, just so that's kind of clear. So we have 0 equals v naught sine of theta minus 1/2 g cosine phi times time. Alrighty, do a little bit of algebra. We have 1/2 g cosine of phi times time equals v naught sine theta. Multiply both sides by 2, divide by cosine of phi, and we get t equals 2v naught sine of theta, all divided by g cosine of phi. So this is the time the ball is in the air. Okay, so we know how long the ball is in the air. If we want to find how far it goes, we just have to plug this t into the x value here, because this tells us how far along the ramp it goes. And we know how long the ball is in the air, so all we have to do is plug t into this guy. Okay, so we have, let's do a different color, I'm getting tired of green. X equals v naught cosine of theta times time. So that's 2v naught sine theta, all divided by g cosine of phi, minus 1/2 g cosine of phi times time squared. So our time will be 2v naught sine of theta all over g cosine of phi, and this is all squared. All right, well, can we clean this up a little bit? Oops, might be worth doing. So now we can say x as a function of time is equal to 2v naught squared cosine theta times sine theta, all divided by g cosine of phi. And then let's see, 2 squared is 4, but we have the 1/2 outside, so that's going to be minus 2. What else do we have? We have, let me check something real quick. This is supposed to be a sine, not a cosine. This should be sine of phi. I was going to say that looked kind of weird. Okay, just making sure we're good. So minus 2 times sine of phi. And then we'll have v naught squared sine squared of theta, all divided by g squared will cancel with one of the g's in the numerator, so you're left with just 1g, times cosine squared of phi. Okay, so far it's just mostly a lot of cleaning this stuff up. We'll go ahead and keep doing it in case you want to work through the algebra. Let's see, what can we do here? Well, x as a function of time. I noticed that this part and this part have a lot in common. They both have a 2. They both have a v naught squared. They both have at least one sine theta. And in the denominator, they both have g. And now I'm going to do something a little weird here. The first term doesn't have a cosine squared of phi, but I'm going to go ahead and factor it out. That way I kill the denominator. So I factored all this out, and what am I left with? Well, at the top, we have cosine of theta that we didn't factor out. And then because I factored out a cosine squared, there's only a cosine to the 1 here. So to get that to properly cancel to where we only have to the power of 1, we need a cosine of phi in the numerator. Hopefully that makes sense. That way, this will cancel with this will cancel with this, and we're algebraically okay. Okay, so there's that. Minus, there's an extra sine of theta on the left-hand side, and there's also a sine of phi that we did not factor out. So that's what we're left with. All right. Now, maybe this doesn't look any cleaner, but we're going to recall one of our trig identities. There's a lot of trig identities here. So cosine of theta plus or minus phi is equal to cosine theta cosine phi minus plus sine theta sine phi. That's my watts going off. Sorry about that if you can hear it. It'll go off in just 2 seconds. Okay, so this is what we have. We have cosine of theta, cosine of phi, minus sine of theta, sine of phi. And what the minus plus is saying here, if you've not seen it before, is that it's just always going to contradict this plus or minus. So if I have a minus here, then I'll have a plus here. If this were a plus, then this would be a minus. Now in our case, we have a minus, so we'll have a plus. So, okay, we can clean it up a little bit. We're left with still what's up front, 2 v naught squared sine of theta divided by g cosine squared of phi. And then we said, well, this is just going to be cosine of our first angle, theta. And then we'll do plus, because we have a minus between them, our second, which is phi. Alrighty, so this, I believe, is what they had up front. This is our range. 2 v naught sine theta, all divided by g cosine squared of phi times cosine of theta plus phi. So there we go. We got that part. And now it wants us to find the maximum range. This will require a little bit of calculus. A quick review. I haven't talked about this, I don't believe, in the calculus section. But, you know, let's just say you have something like this, a graph. The important thing to know is where the slope, or the derivative, if this is the graph f, then when the derivative f prime equals 0, that's our slope, you'll get a max or a min, or you'll get, it's not a very good cubic function, something like that, where you'll also have a slope of 0, but it's neither a max nor a min, or neither. Now in Calc 1, we would take our derivatives and we would do derivative tests to see if it's a max or min and so on and so forth. In this case, we don't have to do that because of the application. You're going to have a max. You're not going to have a min from this. And certainly there has to be a max somewhere. The ball's not going to just go up forever. It's going to come down. We know that the path it's going to take is going to look like an upside down parabola. So it must be a maximum. You're welcome to do a second or a first or second derivative test. You could use either actually. But it's not necessary, and it's going to make the work a little more difficult. Okay, so what we're looking for is the derivative of x with respect to theta. Now, why are we doing dx d theta? Well, just by the nature of the question. We want to find the maximum possible range. Well, the phi is a constant. That's just the ramp. What we want to know is essentially what angle to make. And in fact, it even says, given a v0 and phi, we want to find the maximum range. So the only thing we can kind of play with is theta. So dx by d theta is going to be d by d theta of x of t, which we just saw was 2 v0 squared sine of theta divided by g cosine squared of phi times cosine of theta plus phi. And that's why we're not thinking of this as a partial derivative, because we're assuming v0 and phi are givens, they're constants. Theta is kind of what we're not sure about. Okay, so we need to take this derivative, and hopefully you'll know that this is a product rule, which I think we've talked about. And if you haven't, the way you find the derivative of, let's say you do d by dx of f of x times g of x, that's just f prime of x times g of x plus g prime of x f of x. So we have to take a few derivatives, that's okay. So dx by d theta, derivative of the first, well, the 2 v0 squared is a constant, so is the denominator. The only thing we're really taking the derivative is sine of theta, and the derivative of sine of theta is just cosine of theta. The bottom is a constant, so that stays the same. And then we multiply that by g. So this is like our f of x, and this is like our g. I guess it's g of theta, f of theta. So cosine of theta plus phi plus, actually minus, because we take the derivative of cosine is negative sine. So we'll keep the first, so 2 v0 squared sine theta times sine of theta plus phi, all divided by g cosine squared of phi. Whew, a lot of work. All right. So let's see. We set so now we found our derivative. And like what we said earlier, the max is where your derivative is equal to 0. So what we need to do is set dx d theta equal to 0. So basically we have 2 v0 squared cosine of theta, all divided by g cosine squared of phi times cosine of theta plus phi minus 2 v0 squared sine of theta over g cosine squared of phi times sine of theta plus phi, all must equal 0. All right, well, let's simplify this. I can divide everything by 2v0 squared. I can multiply everything by g cosine squared of phi. And then what am I left with? I'm left with cosine of theta times cosine of theta plus phi minus sine of theta times sine of theta plus phi equals 0. Okay, well that's a little cleaner at least. Now we need to remember a new trig identity. Here's one I'll show you in case you forgot. Cosine of alpha times cosine of beta minus sine of alpha sine of beta is equal to cosine of alpha plus beta, where alpha is theta and beta is theta plus phi. So what we have here, this whole thing nicely simplifies to cosine of alpha plus beta must equal 0. Or, if we combine like terms, cosine of 2 theta plus phi must equal 0. Whew, alrighty. So, a lot of work. So how do we solve this? Well, we know cosine of pi over 2 is equal to 0. So, what we need is 2 theta plus phi to equal pi over 2. And we want to find our theta. So just like how we want to find our x value that spits out the maximum, just so we can go back to relate, what we're doing now is we're finding the x coordinate, or I guess the theta coordinate in this case, that corresponds to our maximum. And then once you have that, you can just plug it back into your function, and voila. Right now we're finding our maximum theta, just so all the steps make sense. So let's see, that's 2 theta equals pi over 2 minus phi. That's 2 theta equals, let's see, pi minus 2 phi over 2. And I could divide everything by 2. And I'm left with theta equals pi minus 2 phi over 4. All right, so when theta is equal to this, we reached our maximum angle. So now that we know that, we need to plug this back into x of t. So this is max theta. We need to plug into x. Whew. Alrighty. So, where is our x? Our x is here. So 2v0 instead of sine of theta. 2v0 squared instead of sine of theta, it's sine of pi minus 2 phi over 4 over g cosine squared of phi. Phi is okay. We can keep that as just that. And then cosine of theta plus phi. So this is times cosine of theta, which we're saying is pi minus 2 phi over 4 plus phi. Alrighty. This is a mess, but it's okay. We can simplify this a little bit. So another trig identity. 2 times sine of alpha cosine of beta is equal to sine of alpha plus beta plus sine of alpha minus beta. 2, sine of an angle, cosine of what'll be a different angle. Let's actually simplify that really quick. Let's see, that's cosine of pi minus 2 phi plus 4 phi all over 4. So that's actually cosine of pi plus 2 phi over 4. Okay. So that's like our beta. So this is like alpha, and this is beta. And we can write that out like this. Okay, so let's see. Now we have this equal to v naught squared, that stays, times sine of alpha, which we said was pi minus 2 phi over 4, plus beta, which we said was pi plus 2 phi over 4, plus sine of alpha, pi minus 2 phi over 4, minus beta, which we said was pi plus 2 phi over 4. And this is all divided by g cosine squared of phi. Whew. Okay. Let's see. This is v naught squared times, these have the exact same denominators, so that's really pi minus 2 pi plus 2 phi. So the 2 phi's drop, and you have 2 pi over 4. You have 2 pi over 4, which is just pi over 2. So this is really sine of pi over 2. Plus, let's do this bit on the side here. Pi minus 2 phi over 4. And then they have the same denominators, so minus pi minus 2 phi. So the pi's drop, and you have minus 4 phi over 4, or minus phi. Okay, so this is actually going to be plus sine of minus phi. And that's going to be all over g cosine squared of phi. Alrighty, so we have v naught squared. Sine of pi over 2 is just 1. And then let's remember sine is an odd function. So I can take that negative, sorry about that, and just put it out front. So this is going to be minus sine of phi, all divided by g. And let's recall that cosine squared of theta plus sine squared of theta is equal to 1. So cosine squared of some angle is equal to 1 minus sine squared of that angle. So I'm going to replace that with cosine squared. 1 minus sine squared of phi. Okay. So we have v naught squared times 1 minus sine of phi, all divided by g times, I'm going to expand this, so this is 1 minus sine of phi times 1 plus sine of phi. We can see the 1 minus sine of phi drops, and then we get v naught squared all over g times 1 plus sine of phi. And there you go. That's your maximum rains. They gave us the answer at the original question. Did we get it? V naught squared over G times 1 plus sine of phi. V naught squared over G times 1 plus sine of phi. So we got it. There's your maximum range. Now, I don't think any of these steps by themselves are particularly hard, but it required that you're very patient and willing to work through a lot of maybe a little tedious problems. Like, you need to know your trig identities. That's important. Maybe I'll even do a video on it. You need to know calculus to take derivatives, product rule. You need to know max and mins and how those are related to the derivative, and you need to know your basic physics, like free body diagram and velocity and finding components and Newton's second law. And you have to be very, very good with your algebra. So hopefully you guys are okay with this. And the next problem is supposed to be the hardest in this section. But the good news is it's the last Newton's second law question in Cartesian coordinates. Then I'm going to have to do a little video talking about Newton's second law in polar coordinates. I don't think I've made a video on that. And then we have to do Newton's second law in polar coordinates. So it'll be